So last lecture we proved that if X is compact and Y is a complete metric space, then the space of functions from X to Y is also complete. In particular, the space of real valued functions on a compact space is a complete metric space. And what we're going to do for the next two lectures is just exploit this fact to see what it buys us in some concrete examples. That is sort of applications of completeness. And these go via the Banach fixed point theorem, which is the subject of today's lecture. So what I want to do before I get to the statement and proof of the fixed point theorem is to maybe explain a little the general philosophy of fixed point problems. I think that's worth doing because, well, you're used to solving equations that look like that, right? You're used to finding an a such that g of a is 0, that is finding a root of a polynomial or some other thing. That's a sort of organizing principle for, much of your life, mathematically speaking. A is either a number, perhaps, or if you're solving a DE, you can put everything on one side, and then A might be a function. You're also familiar with that. The idea, there's nothing particularly special, however, about that kind of problem. Fixed point problems are just a different kind of equation. All right, they look like that. Of course, I can take the x over, and then it's the same kind of equation. Actually, that's the crucial trick in the whole lecture. All right, fx minus x is also an equation. Okay, so what do I mean by a fixed point? So a fixed point, given a function from a set to itself, a fixed point of f, that's just the point that's fixed. All right, so that's a simple enough notion. So I claim there's some advantage to perhaps, even if you start off life caring about finding solutions of an equation, say in real numbers or complex numbers or even a differential equation, there may be some advantage to reformulating it into this kind of problem, a fixed point problem. And the reason why that might be an advantage is easy to explain. So I'll give you some examples of that reformulation in a second. So why reformulate problems as fixed point problems? In case it's not clear, a fixed point problem is to give an x and to give an f and say, what are the fixed points? Do they exist? Are they unique? That's a fixed point problem. Well, that's because it's easy to solve a fixed point problem. First, pick any point. So I'm going to explain how to solve any fixed point problem, modulo some details. Okay, so pick a point. Apply f infinitely many times, the end. Right? Because, look at this, f of f infinitely many times, what's that? That's f to the infinity plus 1. And every first year calculus student really wants to write this down, right? Infinity plus 1 is infinity. Look. I did it, right? Okay, so we can all go home. Okay, so the motto of the lecture is that actually that works. Okay, you all know how to make sense of f to the infinity of something. That's a limit, right? Anytime you see an infinity, it's really a limit. So what does that mean? It really means the limit as n goes to infinity of f to the n of x. And, well, then this identity just works when you make sense of it. So this is not as stupid as it looks. Okay, it does look pretty stupid, though. All right, so, well, we'll go through a few levels of precision. So more precisely, to start with, let's let x1 be f of x0, and in general, xn plus 1 to be f of xn. Well, what would we need to make sense of that argument in the standard way we make sense of infinite sequences and convergence and so on? Well, we'd need some metric on X, for instance. So suppose X is a metric space. And that, well, f to the infinity of x makes sense. That is, that the sequence f to the n of x0, i.e. xn, converges. And let's call the limit x star. Okay, so that's a sensible thing. So that x star is what f infinity x is supposed to mean, right? Okay, well, what do I need? I need actually a condition on f for that nonsense to become meaningful. And all I need is continuity. So suppose also that f is continuous. Well, then what does that actually say? It says f x star is f of the limit of that. But we know continuity, at least between metric spaces, is precisely the condition that you can take limits out of the function, right? So this is totally legit, since f is continuous, to write this is the limit as n goes to infinity of f of fn of x0. Well, that's of course just the limit of the sequence, which is f to the n plus 1 of x0. That is, it starts when n is 0 at f1 of x0. But you know, the original sequence, which starts at f to the 0 of x0, and this one, which starts to f1 at x0, I mean, they're the same sequence. They're just shifted by 1. So they have the same limit. They both converge or diverge. In this case, they converge. So that's the same limit, right? That's the limit of fn, which is x star. Okay, so that wasn't so stupid after all, right? That's literally just what we did. Made sort of sense. Okay, so well, solving fixed point problems is easy, provided we know that that converges. I mean, f being continuous, I guess we can believe that, you know, our equation, the thing we're trying to deal with, is probably continuous, so that's innocuous. It's more of a constraint that this thing converges, and to ensure that, we're going to assume some property of f, namely that it's a contraction mapping. I'll define that in a second. But under that condition, this will work and produce a fixed point. All right? Okay, so you believe, modulo those conditions, that solving fixed point problems is easy. Now let me convince you that you can convert interesting problems into fixed point problems. Because you're not born necessarily knowing any interesting examples of that second kind of equation, right? The main example will be solving DEs next lecture, where I'll write down a fixed point problem which encapsulates finding solutions of an arbitrary first order ordinary differential equation. But let's start with a simpler example, which is Newton's method. Okay, which is a typical example of this first kind of equation, right? So you're given a differentiable function, and let's just suppose, we can restrict to some domain if necessary where this is true, but let's just suppose that it's never 0, the derivative. And the aim is to find a root, right? We want to solve GA equals 0 for A. Yeah? So Newton's method says, well, take a guess, x0, and then iterate the following equation. And And then the idea is that that's supposed to converge, well, you know. So, I mean, that equation says just go above x0, for instance, draw the tangent line, see where it hits. That's x1. That's what the formula says. Then go above x1, draw the tangent line, see where it hits, iterate. Well, that's what the equation says. Okay, then, you know, if you're lucky, that sequence converges to a root, as you can see in the picture. Okay, so that's a typical way of solving that kind of equation, but that's easily rephrased as a fixed point, right? Because consider the function which is just the right-hand side, x minus gx on g prime x. Then we've got GA being 0 if and only if f of A equals A. Right, if GA was 0, I'd get f of A equals A and vice versa, because I'm assuming this is non-zero. Okay? So this converted the problem of finding a root of one function, g, into the problem of finding a fixed point of a different function, f. Okay, that's possible in many cases. So there's many cases of interest where you're trying to solve an equation, you can convert it by some trick to a fixed point equation. And then, well, you can solve fixed point equations, so good for you. All right. Okay, so I said that I want to give you a condition on the function f, which in such a situation will ensure that that sequence converges. Well, actually, that's a bit of a lie. So the condition I'm going to give you ensures that that sequence is Cauchy. We also assume that x is complete, and therefore it converges. And that's where this business comes in, right? So we have an example of a complete metric space, so we have an example to which we can apply this. And that's what we'll do next lecture with solutions of DEs. All right, so let's set up the fixed point theorem. The condition I need to take on my f, which ensures that that f to the n x0 is Cauchy, is that f is a contraction. Okay, so we've seen similar things before, right? When we talked about, isometries which preserve distance. This is a relaxation of that. It says that the distance is decreasing and by a fixed amount. So there's a fixed gamma between 0 and 1, sometimes called the contraction factor, such that for any pair of points x1, x2, the distance between their images is less than or equal to gamma times the distance between them. Right. So such a map is called a contraction. I didn't say f was continuous. That follows immediately from this equation, right? So it's automatic. So any contraction is continuous. I mean, in fact, uniformly continuous. Right, so that's the condition we need. Okay, so theorem. let X be a complete metric space, and F a contraction. Then, so two statements. Then F has a unique fixed point. And moreover, this iteration works. Well, we're not surprised by that. I've already explained why that had to be the case. And for any x in X, the sequence f to the n of X converges. It's called the fixed point X star, converges to that unique fixed point. Okay. So well, we have to prove existence and uniqueness of this proposed fixed point. Uniqueness we'll do first because it's easy. I mean, the proof itself is not very difficult compared to some of the things we've tackled. So let's do uniqueness. So suppose that P and Q are fixed points. So we need to prove they're equal. Well, the distance between them, I mean, I want to argue that's 0, right? That'll show they're equal. And I know how to compute the distance between them because that's Fp and that's Fq because they're both fixed points. And now I just use that it's a contraction. So throughout the proof, gamma will be a contraction factor for F. Well, that's impossible unless that was 0 to start with because gamma is less than 1. Okay, so if a fixed point exists, it's unique. We just need to do uniqueness. So what we're going to do is show that that sequence is Cauchy. Then we know a limit exists. And then this argument proves that it's a fixed point. Okay, so choose any point x. That's our x0. I might as well call it x0, I guess. Right, so we claim the sequence xn is Cauchy. Well, so we need to understand what the distance is between xn and xm for a pair m and n, and we might as well assume that m is greater than n. Well, given we just discussed this, you should maybe be able to see what we're going to try and do. We need to prove that's small, right? And we know the things involved are f to some high power applied to x0. So we can use some argument like this to pull out gammas. Well, since there's powers of f, we can pull out powers of gamma. The powers of gamma will get smaller and smaller, and then we're done. So that's what we're going to do. So the first step here is just to use the triangle inequality several times. So we can write that as less than or equal to. And I didn't actually officially explain using the triangle inequality twice, say. I hope it's pretty clear that if I go dxy is less than dxz plus dzy, and then I just do it again, use the triangle inequality there, dxz z prime plus d z prime z plus d z y. I can just continue in this way. Right? Okay, so I just do that however many times are appropriate. So just split it up into consecutive terms of the sequence. All right. Now let me write out what those are. So that's f to the m of x0, f to the m minus 1 of x0, okay, but notice that if I applied f twice in that argument over there, well, that's f of x1 and f of x2, so I can take out a single gamma and still be left with fx1, fx2, and then I can take out gamma again. All right? And by induction, I can do that however many times I like. So in particular, in this case, I can take m minus 1 out of both of them, and I'll be left with a gamma to the m minus 1, and there'll be a single f left there, and none left there. Here I'll get a gamma minus 2, same thing, all the way down to a gamma, n. Well, there's a common factor there, right? So that's just this sum from I equals n to m minus 1, gamma to the I times that number. Whatever that is, I don't care. It's fixed anyway. And what am I trying to do? I'm trying to make this small, provided m and n are sufficiently large. That's the whole point of Cauchy, right? So I don't care about a constant factor. It doesn't matter. As long as the other part is getting very small, provided, well, n is large, because that'll force m to be large. Okay, so I just have to work on this part there. Well, there's a common factor of gamma to the n, which I can take out. Well, I don't have to necessarily. Anyway, so let's do it. So that's then I from 0 to m minus n minus 1. Right? Okay, so now I'm in business because, well, that's adding up the initial part of an infinite series which I know converges, right? Because gamma is less than 1. So that's, and there I've got an n, and I make that large, and I'm going to make the thing small. So I'm in good shape. So that's less than or equal to gamma to the n. If I just take the bound, the upper bound to infinity, that's got to be bigger because gamma is bigger than 0. Well, that was equal. I apologize. That was just factoring out gamma to the n. And then this I'm summing over more things, so it's less than or equal to. And that's 1 over gamma. That's just a geometric series. Well, so we're done, right? Because given an epsilon, we can make this quantity down there less than epsilon by taking n sufficiently large. Right? And then that shows that by just taking that n for all m, So that would be my capital N, whichever capital N makes that less than epsilon. And then I take little m and little n greater than or equal to that, and I'll have the condition for the sequence to be Cauchy. All right, so this shows the sequence is Cauchy. Now, since x is complete, it has a limit. Okay, so there's an x star, and then we're done, right? Because, well, come back over here. F was a contraction from x to x. X is a metric space. Contractions are continuous. So I've got my continuous function. I apply that to the limit. F is continuous, so that means I can take the limit out, and then this argument goes exactly as I outlined to show that x star is a fixed point. By the earlier argument, x star is a fixed point. Well, I already know fixed points are unique. So the only other claim was that for any x 0, that sequence converges to the fixed point. Well, I constructed the fixed point as the limit, and since the fixed point is unique, it didn't matter which x0 I chose, so that's also done. Okay, so that's the fixed point theorem. That's a really great theorem. I mean, it's not very difficult, as you've noticed, but it's just slick. And the ratio of work in the proof to the astonishing array of consequences is very satisfying. Any questions about the proof? Okay, so maybe what I'll do is spend a bit of time talking about one application. So the main application I'm going to sketch is Picard's theorem, but I maybe want to do that as a whole, starting from the beginning of next lecture. So what I'll do now is talk about the Bellman equation. Okay, so this is, I would say, a very topical application of the fixed point theorem. So how should I put this? Okay, I promise that makes sense. Well, you know, most things playing Atari games had brains until, you know, what, 5 or 6 years ago, when DeepMind wrote a computer program which plays it better than people. Yeah.
Sorry, why was it again that x star is the same for all x?
That was by uniqueness, right? Because suppose I took one x0 and some other x0. Well, this sequence, I proved that for any choice of x0, the second part of the proof was for any x0. So I took any x0, I proved that sequence was Cauchy, and therefore it has a limit, and then that argument showed that it was a fixed point. So it didn't matter which one I started with. So I know I get to some fixed point here when I take the limit. Take another initial point, apply f to it. Then that also has to converge to a fixed point by the same argument, and then by uniqueness, those are the same, so it doesn't matter. Okay, so, you know, the joke with Atari is that people figured out how to play it with reinforcement learning, And reinforcement learning is an algorithm for searching a space of policies for how to play a game. That is, I see something on the screen and I choose from a certain discrete set of actions. That's a policy. A policy is a function, so I'm searching over a space of functions for something that does what I want. Well, space of functions are complete. I can apply the fixed point theorem. And that's actually what is behind reinforcement learning, in principle. So the theoretical basis of reinforcement learning and optimal control and so on is something called the Bellman Equation, which is an application of the fixed point theorem to the space of policies. And I'll try and explain that briefly. Okay. So in practice, well, okay. Okay, so I need to set up some language. In the end, it'll just be some set of functions, but the language is important for setting up the actual equation. So the problem is the following, as the example of Atari suggests. So consider an agent. Well, that's the person playing the Atari game, or the system playing the Atari game. In an environment, the environment is the game itself, the software which is interacting with the agent. The agent chooses actions, and those actions cause the agent to transition through states. Right, so states, actions, transitions. Okay, so S is going to be the set of states of my agent. And let me give a simple example. I mean, in the end, this is a non-trivial sort of piece of math that we end up with. So the example is the following. So let the set of states be Z. Okay, so you're thinking of an agent which is moving along a line. So let A be the set of actions. So, well, let's say move left, move right. It may be, I mean, in this case, no matter what state I'm in, I can always choose the same actions. But suppose there was a boundary at the left. Then in some states, that is for some integers, I wouldn't be able to move left, right? So we want to allow the condition that the set of allowed actions depends on the state. That's what this means. So A of S is the set of actions available when the agent is in state S. Okay, what about the transitions? Well, what does this mean? It means that the agent's in some state, it makes some action. That's an interaction with the environment. Something happens. The agent then transitions to a new state. That's described by a probability distribution for a reason I'll describe in a moment. So this is the conditional probability of the agent transitioning to state S prime given action A in state S. Okay, so there's discrete time. At each time the agent is in some state, it makes some action, and then given that pair, the state and the action, there's some probability of each possible other state. I'm going to assume for the setup that this is only non-zero for finitely many. So I'm going to assume that for every S, this is finite. Sort of reasonable. Right? At any given state, there's only finitely many things you can do. And this is non-zero only for finitely many S prime. So in a given state and with a given action, there's only finitely many possibilities for what you might transition to. Okay, so let me give two examples. So this P is sort of the model of the environment, right? So something happens in the video game, you don't quite know what, and the P encodes exactly this information about what transitions are going to happen. All right, so here's one possible model of the interaction between the agent and this lattice, which is I try to move right, and I move right. I try to move left, and I move left. Okay, so that's 1. If S prime is S plus 1, and A is right, and 1 if S prime is S minus 1, and A is left, and 0 otherwise. Okay. Well, why is it a probability distribution? Well, because, you know, if the agent could always achieve every action that it tried to achieve, then it wouldn't be a very realistic environment. So you may want to have it that instead, when it tries to move right, sometimes it fails and stays still, right? So in that case, I would replace this by a half, and there would be a half for if S prime equals S and A equals right. That would represent I tried to move right and I failed. And then I could put a half here and add a half, which is F prime equals S and A equals left. 0 otherwise. Okay, in general, that's the situation. So that's why it's a probability distribution. All right. Well, so what's the problem? That's a lot of definitions. The problem is, give the function from states to actions which achieves the greatest reward. Well, I haven't defined rewards yet. But, well, some of the states are preferable. For example, the one where the screen says you won, right, in an Atari game. So you get some points for that. So we also assume given RS. Okay, so for every state, there's some intrinsic reward associated to it. That's part of the problem. And, you know, for the usual reasons in all of this, I need to assume this set is bounded, right? That'll be important in setting up the fixed point theorem. So the set of possible rewards is a bounded subset of R. S may be infinite, right? S could be infinite, but I'm assuming A of S is finite for any S. Okay. Okay, just one more piece of definition, and that there is a discount factor. So rewards attained now or in the near future are better than rewards obtained later. So we discount future rewards by some amount. Okay, so what is the... So what can I do? My agent, say on the line, well, what reward should I take here, for instance, so that it's bounded? Let's make it so moving to the right is winning, right? So that is, we take RS to be something like, well, I could say e to the s, but that's not bounded, so let's just truncate it at whatever, some number. Okay, so clearly the agent wants to move to the right in order to accumulate lots of points. So, well, what is a behavior? A behavior is a sequence. Well, the trace of a behavior is a sequence of states. And the discounted reward of a sequence of states with discount factor gamma is given by that. Right? Okay, so what am I trying to find? I'm trying to find a policy for behaving in this environment, this sort of problem, which is the setup which is described by P and R and S and A. So that is, given a state, I need to choose actions, right? So policy for action, well, it's a function, pi from the set of states to the set of actions, such that for all S in S, pi of S is an allowed action. Okay, so what is the reinforcement learning problem or the optimal control problem? It's the problem of determining the pi such that when I follow that pi, this is as high as possible. Right? So that's an optimization problem over the set of policies. And we can solve it. Theoretically, at least. So it gets a bit tricky to solve. So that's why it's sort of clever, the Bellman equation. So if you just sort of follow your nose there, what are you going to do? Well, you're going to sort of look, you want to search over all policies somehow, right? And suppose that pi star was a best possible policy, that no policy was sort of, by making a different set of choices in a different set of states, could beat that one. Well, I don't really want to make precise sense of that, because I don't need to. That's the whole magic. But that sort of makes sense, right? You could imagine something like an optimal policy. And then if you had an optimal policy, so the perfect agent at playing this game, you could define the intrinsic utility of a state to be the expected discounted reward that that perfect agent could get by following its policies starting in that state. Right? That would be the best, the most you could possibly extract from that state. Right? So that's the expected value of that thing. And what is it the expected value over? Well, it's the expected value over all sequences of states. This is a random variable because the transitions have probabilities in them. Right? But that's the most you could expect to extract from an initial state with S0 equals S. Okay, but don't worry about that because that's impossible to figure out anyway. So we don't do that. Instead, note that such a function, which is called a value function, for the obvious reason, it tells you the value of any given state. Well, what's it a function from? It takes states to real numbers. And it's a solution of the following equation. And if it is derived from an optimal policy, you can check, if you think about it, that it must be the case that this equation is true. What the hell does that say? Well, it says the most I can extract given an optimal policy from an initial state S is the reward I get for just being in S. And then, in the next step, the well, what's the best I could get in the next step? Well, it's the maximum of all possible actions starting from here of, well, the expected value of the best possible amount I could get from all states I can reach from the current one, right? And that's what gives you the expected value. Okay, so that's a totally reasonable equation. It's not clear you can solve it, right? Because, for example, to solve it, maybe you had to figure out an optimal policy. So it's not clear you can solve this equation, just the way I've written it, but it makes sense. But we can solve it, because this is a fixed point equation. Right? Look at it. I took a u, and there's a u. So let x be the set of all functions from S to R. Give S the discrete topology, and take bounded functions. Okay, so I mean, continuity doesn't say anything because this is discrete, so this is just functions from S to R, and take those that have a bounded image. That's a subset. It's a complete metric space. And here's a contraction mapping. Take the U, which is an element of X. That's a value function. So take the value function, get a new value function, which assigns to S the right-hand side. For any u. I don't know it's optimal or anything about it, but that is a totally legit equation which sends a bounded function to a bounded function. That's a complete metric space. You check it's a contraction because that's less than 1. Okay, so Banach tells you that that a solution exists, a solution to the Bellman equation, and then you can use the u to go back and define what an optimal policy is. It just follows that value function. All right, so from the Banach fixed point theorem, you can derive, at least theoretically, the policy which is optimal for playing in that environment. And, well, in practice, of course, I mean, it even gives you an algorithm, which is iteration of f. In practice, that's too slow, so people don't do it. But you substitute some other approximate method, and that's how reinforcement learning works. Okay, so I'll have to stop there. It's over time.